Okay, let's talk coordinate descent. So the idea behind coordinate descent is we're going to take our unidimensional approach for optimization. So far we've learned optimization based on root finding. Okay, we did the Newton-Raphson, and we said, you know, if you take the second derivative and you take the derivative of the function and then you set that equal to 0, basically you can find local mins and local maximums. And then we said any of the root finding methods that work on a derivative will work. We also talked about golden section search, right, as a way for unidimensional optimization. Sometimes you have a function of more than one variable. And so coordinate descent allows us to find the minimum of a multivariate function. Allows us to find the minimum of a multivariate function by minimizing one variable at a time. Iteratively. Okay, and here you can replace the word minimum with maximum. It doesn't matter. Okay, if let's say you have a function you want to maximize, and your algorithm can only do minimums, the easiest way to do it is just take that function, multiply it by -1, find the minimum of that, and then it's the maximum of the original function, right? So to maximize a function f, okay, let g of x equal negative f of x, then minimize g. Okay, so the way this looks is, let's say you've got some kind of 3D surface, right? So let's say, are you guys familiar with contour plots? So it's like you have this, imagine having like a landscape, okay? That your function forms some kind of surface, right? Your function forms some kind of surface, and then you have, you create a model of it, and then you put it in an aquarium, and then you pour some water, and then the water comes up, like, I don't know, maybe this is the worst explanation ever, right? So this is like my terrible drawing here, okay? So here's our aquarium, and you've got some, landscape here, right? And then you pour water in, and so the water comes in, and then basically it's going to trace out a line on the surface here, like this. Okay. Okay. And so at each level, right? You do the water, and then you go up, add a little more water, and you trace the line, and so the resulting plot will be something like. This is a terrible thing, but okay, and so you get it kind of an idea of, you know, what this surface is supposed to look like. Okay, so anyway, let's just start off with a simple contour plot. Okay, now it's just going to be a bowl. All right. So this is how coordinate descent will work. So let's just do a simple example. What is this called? A paraboloid example? I don't know how to spell paraboloid. Okay. Is this an O? All right, whatever. Okay. All right. So basically, you've got like it's just this shape here, right? And I'll go ahead and I'll like trace out some. Okay. And the way and so our contour plot will look something like a series of ellipses. Maybe this will look too. So okay, so I got these ellipses, and so this is our plot in 3D. And the way this works is you just start at some point. Okay, so you'll start off with a kind of an x0 and a y0, and you're going to lock one of these variables. Okay, you're going to set x0 to a constant. Okay, and so originally we started off the paraboloid. We have a function of x and y. It's a function of two variables, but once you set x equal to a constant, it becomes a function of just y, right? So you're going to basically, you set x to a constant. Okay. And so you have f of x equal to x0 and y, and so this just becomes a function of y. And so what that basically looks like is it's like drawing a slice right through right here, okay? And so if I can illustrate this over here, it would be like drawing a line, cutting a plane right through here. Okay, and when we do this, it traces out basically just a slice along here, okay? So there is basically a line right here along this plane that we're cutting out, okay? So when you trace this, it cuts out this, the plane cuts a slice right through the paraboloid, like that, okay? And so, so now, if I take a look at this, all I do is I just try to find the minimum of this function here. Okay, so we just find this minimum. All right, and so when we do that, that's going to end up being this spot right here. Okay, so so we find the value of y, find the y that minimizes this function. Okay, and then so now at our next iteration, I'm going to go ahead and just copy this. Okay, so we start off with this, and now I found this. So this is going to become my y1, right? So we find so we start off f of x and y. Okay, set x equal to x0. This becomes f of just y. Minimize, find the y that minimizes this using a unidimensional method. And then so now update your coordinates to x0 equal to x equal to x0, and y will be y1. Okay, so you have now this, and then you just continue, and you set y equal to y1. Okay. Set y equal to y1, so f of x and y, now that y is set to a constant, this will become a function of x. Okay. And so if we draw our paraboloid again, it's now a paraboloid going in, we still have this thing. Okay, but now our slice goes, our slice now goes this way. Oops. We run a slice through here, and effectively we're going to cut a piece right here. Oops. Okay, so we cut a slice through our paraboloid right there, and now we're going to try to find the minimum right here. Okay, so now that we have our plane this way, we have this function, and we're going to find the x that minimizes this. Okay, and so when we do that, that will probably end up being something like right here. Okay, and then we will update. We update our coordinates to x1 and y1. Okay. And then you repeat the process. Okay, so now that you have this, then you will lock that into place, turn it into a function of y, and you'll kind of just repeat, and you'll just continually kind of minimize back and forth, you know, something like this, and you just iterate again and again and again, and then eventually it should take you to the minimum. So coordinate descent, it's called coordinate descent because you're basically updating one coordinate at a time. You set your function, all of the other variables to be constants to reduce a multi-dimensional function to a function of one variable. Now that you have a function of one variable, you find a minimum using any of your optimization methods. I mean, you could even use just good old-fashioned calculus and take the derivative and set it equal to 0 if that's easy, right? You do that, you find the minimum, and then you just repeat this process iteratively, doing one dimension at a time. If you have 5 dimensions, you do the same thing. You'd set 4 to a constant, so it reduces to a variable of 1 variable. You find the minimum of that, then you lock that into place, unlock the next variable, lock the other 4 in as a constant, and repeat, so on and so forth. Okay, we'll end here for today, and thanks for being patient with me as we did the attendance roll call and everything. And we'll see you guys on Wednesday.